Okay, hello everyone. Welcome to this week videos. For this week tutorial, I'm gonna do a simple simulation on the open cycle steam turbine process. I plan to use my Aspen Plus software actually for this particular simulation, but I still have issues with my Aspen Plus license, and it's gonna take a while for me to get it renewed. So for the time being, I'm just gonna use whatever I have, which is the open source process simulator. In this case, I'm gonna use a DWSim software. So yeah, let's begin. I'm gonna do a little bit of introduction, but not too detailed though. So basically, when it comes to generating powers, generating electricities, we're gonna use a turbine, okay, or expander. The common one would be, the steam turbine commonly used in the thermal power plant. As you all know, this is just a basic description of the steam turbine. So steam turbine is basically a device that extracts thermal energy from a pressurized steam. So it really depends on the system. You can have like a supercritical steam, ultra supercritical steam system power plant, or maybe subcritical system power plant. So basically that energy from the steam will be extracted, and there's going to be expansion of steam when it enters the turbine, and it's gonna rotate this output shaft. So this output shaft will be connected to an electrical generators to produce electricities. I'm not really a physicist or whatever, but if you really want to learn about how, okay, this rotating motion, okay, over what is it called, this over shaft, and then the application of magnet and as well as electromagnet, okay, to create electricity, I really suggest you to go and visit these videos. The link is in here. They provide a very good explanation on how, okay, electricity is generated from the use of electromagnet as well as permanent magnet. Yeah, for this particular process, as I said, we're going to simulate the open cycle steam turbine. Actually, this process, I took it from this example, okay, flow sheet from DWSim software itself. I think this is developed, I guess, this example problem, or maybe example simulation was developed by this Rohan Adhikari S from the National Institute of Technology, Karnataka, India. So basically, I just download the example and then read the description. So I extract all of the necessary information. So these are the design problem that I took from the document. So we have water around 18.3 degrees Celsius. It's quite cool though. I don't know why, but doesn't really matter. At 1 atmosphere, around 907 kilogram per hour is sent into a pump to increase its pressure to 17 atmosphere. And then this high pressure water is heated into its boiling point to 205 using a boiler. This one, inside the first boiler, they're gonna generate like this super, what is it called? I really forgot what's the name of this steam. Saturated steam, yes, now I remember. And then this steam will be superheated to 287, okay, at the same pressure, to ensure that condensation of the steam does not occur in the expander, which is your turbine. And lastly, the steam is sent to a turbine, which they expand adiabatically and rotate the shaft to produce electricity. If you want, actually in the document they don't really mention in details, okay, what are like the description of what is steam turbine and its working principle, things like that. But in the document you will see that this is the main I'll say information that you can get from the document. Okay, moving on. Yeah, this is basically the same design problem. But in here, there are a few questions that I would like to ask, or I would like to answer actually. What is the energy input and output when we heat up the steam or water to turn it into steam and to turn the saturated steam into superheated steam? And then what would be the energy that we, when we invest the energy, what are the energy in form of electricity that we can get? So that translate into the efficiency of the process itself. And then is there a way for me to improve the process? So based on this design problem, if I really want to simulate this in my DWSim or any process simulator, this is the process flow diagram. So as usual, I have a low pressure water going to pump and then go to heater, which is to heat it up, okay, into turning the liquid water into super saturated water, and then superheat the steam and then expand in the turbine. So this the basically how the process looks like in DWSim, which I will demo it later. A few things that I really want to discuss here, even though we have a heater 1 and heater 2 in our simulator, in reality, okay, the way I see this, in reality, they are one single unit. Okay, why I say that? Okay, this is an example of steam boiler to generate basically steam, normally to produce electricity, I guess. Where where here we have a steam drum, and then we have water here coming down, and then there's going to be, and then it will be distributed along this I would say a column, I guess, or maybe this region where you have a fuel that will be ejected here. So you have a flame here, and there's going to be a lot of tubes here. Okay, the water will be in a tubes, and then whatever, and then the water that at this area will be subjected to what is known as this direct heat. Okay, where the heat will be transferred, direct, and through radiant heat. Okay, this water will turn into superheated, saturated water, and then it goes into a steam drum. Steam drum will, so basically this part is the heater 1, and then steam drum will separate saturated liquid, and then saturated what is it called? Saturated vapors, and these saturated vapors will be further heated or superheated, okay, to form superheated steam, which is heater number 2. So if you think that this is a 2 unit, this is a 1 unit. It's just that the first part here, they are subjected to a direct heat. Basically, you really have a flame, and then like we cooking, like we cook our water, right? So whatever heat that are on the used to boil the water, that's direct heat. And then whatever hot air, okay, is then the hot air will travel upwards, and then it will hit this is still the hot air is still quite hot, by the way. It's not that cold. It's not cold. So they're gonna heat up this saturated vapor to form superheated steam. So this superheated steam will enter a generator or turbine, okay, and it will expand. That's number one. Number one. Okay. Number 2, if you see here, there's within the same unit, you will have what is known as the economizer. Economizer is basically just a fancy way, I guess, of saying we don't want to lose this heat. We're gonna use as much heat as possible. So this whatever leftover heat or hot air will be used to preheat, okay, the incoming boiler feed water. So we're gonna extract as much heat as possible, okay, into from the hot air or from the fuel into the boiler feed water. Okay, that's number 2, economizer. And then, as I said, they goes into after economizer, they will go into this this tube, I guess. Some people call this like a many tubes, okay, surrounding this area as some people call this as a water wall. So the second one basically turn the hot water, I guess, okay, slightly hot boiler feed waters into a saturated steam, or saturated, yeah, saturated steam, and then goes to here, and then the next one you have a steam drum, and then the next one you will have a superheater, and then here you will see that this part is called a reheater. What does it mean by a reheater? So basically, after the superheated steam, okay, this will go into a turbine. Based on my reading, some turbine does not only have like one single turbine, they have like a high pressure turbine system, medium pressure turbine system, and then low pressure turbine system. So after they enter the high pressure turbine system, so the temperature will drop. So as opposed to go to the medium system, medium pressure turbine system, so instead of using that slightly lower temperature steam, they send it back, okay, to this boiler to reheat the steam before it enters to the turbine again. So basically this is just to extract as many heat as possible, and then to make sure that the efficiency is always high. Because if you learn thermal, you know that based on the Carnot cycle, right? Carnot engine or Carnot, Carnot engine, I guess. Efficiency is basically 1 minus TC over TH. Basically, the efficiency is really depends on the temperature of the of the heat sink as well as heat source. So you always want to make sure that your steam is always at high temperatures. Okay, okay, what's next? So yeah, basically we're gonna input this in our simulators and then see what happens. A few things that I want to highlight here is we're gonna use the steam table property method. Am I missing anything? Probably not. So yeah, let's go to our DWSim software. Okay, I have opened my DWSim software. If you realize, my last videos, in my last videos, there was a slight change in the interface, but overall they are the same. In my last videos, the version is version 6, I think, but now they have slightly updated the software, and right now I think it is a version 6.6. So there's going to be a slight change in the interface, and there's probably a lot more things that they change or they upgrade or update, but yeah, feel free to explore. Moving on to our simulation, as usual, I'm just going to create a new process simulation model. Okay, this one will pops up. Just hit next, choose your material or chemical, just type water and then hit enter. They will check, meaning that it has been added. Go click next and then go down. I'm just going to choose a steam table property method, and then I'm just going to choose this one. I don't know what is this version to. Maybe there's a slight upgrade in this steam table database or things like that. So hit add, hit next. This is just a unit, SI unit for reporting and things like that. So I'm not going to change anything. So hit finish. Okay, right now, first thing first, I'm going to close this guy. And then I'm going to make this one slightly bigger. So here we are at the flow sheet interface, I guess. Okay, I'm going to begin with the pressure changer. So I'm going to add pump, and then I'm going to add exchanger, heater 1, heater 2, and then lastly, I'm going to go to the pressure changes and then add expander or turbine. So I add my material stream here, 1, 2, 3, 4, 5. Okay, to run pump, I need energy, so I put here. To heat up, I need energy. Okay, to heat up also, I need energy. Expansion produce work. Also, you need to add energy stream, but there's going to be like a reverse, I guess, reverse sign or reverse arrow. You will see later. Okay, first thing, I'm going to rename this guy. This one I rename as LPH2O. Oops, it's not. Okay, never mind. This one E1, enter. This one is LPH2O, enter. This one is HP, high pressure H2O, enter. Okay, this guy, E2, energy 2. This one is energy 3. This one, because turbine for this work, so I'm going to use a different one, maybe W for work. So low pressure steam go to pump, become high pressure steam. Oh, there's a typo here, HP H2O. And then heater gonna heat up the high pressure water, turning it into steam. Okay, steam will go into a superheater, turning it into a superheated steam. And finally, it will be expanded and it will become a low pressure steam. I'm not going to rename the process unit because I don't think it really matters. So I'm going to set up my, what is it called? My feed first. The water enters around 18.3 degrees Celsius. Pressure 1 bar, mass flow is 907.2 kilogram per hour. Okay, everything will be updated automatically. Compound, no need to change anything because I just use water. Okay, next I'm going to go to pump and then I'm going to connect all the inlet and outlet. So inlet will be LP, outlet will be HP, energy stream will be E1. And then pressure increase. So the water will be, the pressure of the water will be raised from 1 bar or 1 ATM to 17 ATM. So the pressure increase will be 16 bar or 16 ATM. So the pressure increase will be 16 ATM is 16 to 1200 Pascal. Yeah, I'm just going to leave the efficiency around 75%. Okay, next I will move on to the heater block. So just click the heater block. Inlet stream will be high pressure water, leave as a steam. Energy will be E2. And I will specify outlet temperatures. So the water will be heat up into a saturated steam with no pressure drop, and then the outlet temperature is 205 degrees Celsius. Okay, moving on. Heater block number 2, just click this guy, and that inlet will be steam, leaving out as a superheated steam. Energy stream will be E3. Yeah, outlet temperature will be 287. 287.8 degrees Celsius. The heating process will have no pressure drop at all. Okay, lastly, we'll have expander. Just click this guy. Inlet stream will be superheated steam. Outlet stream will be low pressure steam, and then energy stream will be W, which is work. So you will see that they have a different tail, or whether this line will enter on the tail side or whether it exit at the head side. Calculation type, outlet pressure, okay, they will be expanded adiabatically. Outlet pressure is 1 bar, efficiency 75%. I'm not going to change anything. So basically, I'm pretty much done. I will close everything. Maybe I will zoom in a bit. So I will solve this flow sheet and then see what happens. So it's calculated, and then it's already been it was calculated successfully. Okay, what I care here for my process, what I care is the energy investment and what are the energy output. The rest are, because this is just a physical process, heat up, cool down, no reaction. So the mass in is equal to mass out. So I'm not going to bother with the mass balances, but I really want to see what is the energy required, energy usage or energy invested. So here I will go to result, and then I will create a report. Here I will select energy stream only, E1, E2, E3W. So I will view report. So this is my report. Okay, the energy requirement to run a pump is 0.54. To heat up the water into saturated steam, 684. To superheat, 552. And then lastly, work produced is 101 kilowatt. So I'm going to use this information and put them in a table so that we can compare what is the DWSim, okay, result produced by, you know, the person or the guy who created this example versus mine. So yeah, let's move on. Let's go back to our presentation. Okay, if you see this table, okay, the one on the right hand side is mine. This one is the example that the developer of this as an example process result. So you see they are all the same, nothing changed. So result wise, they are okay, I guess. Here the thing that I really want to comment here is, yeah, sure, comparable result, because you know because the condition, I just follow the condition like exactly, so I would expect the result to be the same. The second thing that I really want to comment here is the efficiency is rather low. Okay, we invest around 700, I guess, around what, 700 kilowatt of energy, but it gives us around 101.3 kilowatt of energy of work. So around 14.7%. We got only like 14% of energy invested. Now, this is not really surprising given the fact that the system, okay, operates at relatively low pressure, 17 atmosphere, and the temperature is around 287. And we all know that using this equation, if you want to have a higher efficiencies, you can just always go higher heat source. So when you have a higher heat source, the denominator part will be bigger, this term will become smaller, so the steam become larger. And in fact, I took these numbers from these papers by Zhang Tongjun, okay, Journal of Physics in 2020s. They say for a power plant that operating under subcritical condition, efficiency is 38, supercritical 41, ultra supercritical is 44. And then if you think about it, right, 38, 41, 40, 44, I was like, yeah, who cares, like 4% increase, right? But you have to think about this. Now, in power plant, we are producing, you know, the conventional power plant, based on my reading, they operates like 1 gigawatt. Okay, they produce around okay, this is just a number based on what I read. Okay, produce around 1 gigawatt to 10 or even larger. There are some power plant that I Google. They have a capacity or output around 50 gigawatt. Okay, so there's a lot. So even though the increment in terms of percentage is very low, given the fact that the amount of energy that you produce is very these differences, okay, can can lead to a different can give us a drastically different, like a money, I guess, or profit. So same goes with I have my friend. He said that he's working in the catalyst company, okay, doing the cracking unit. He said, oh, their team are so excited when they have like 0.5% increase in efficiencies in their catalyst. Now, well, to a normal person, 0.5% increase in the catalyst efficiency, that's pretty much nothing. But given the fact that, you know, people operate cracker a lot, and then the amount of crack product, or the amount of, you know, fuel, or the amount of raw material being used, okay, in the cracker unit is a lot. So 0.5%, okay, is huge in terms of total like the true amount being processed or being produced. Same goes with this one, given the fact that the steam turbine, the conventional, is generating around 1 gigawatt or and above, okay, of energy. There might be a smaller version, but I'm not going to talk about that. But you know, the conventional one, they have around 1 gigawatt. They are producing around 1 gigawatt of energy, okay, increasing by 3%. That's a lot. So that's one way for you to increase the efficiency. Now, 287, okay, people might be thinking, oh, hey, if I increase temperatures, don't you think that the material might not be able to withstand that high temperatures? But if you see here, okay, GE and Siemens, they are a producer, they are manufacturers of steam turbines. So if you see here, this is the Siemens example of the Siemens steam turbine. Okay, they can run around 80 bar, and then inlet temperature around 565. So definitely they will get a higher efficiencies. Same goes with this one. Okay, this one, I took this one from a GE brochure, where, you know, same, around 540 degrees Celsius steam, and then around what, 140 bar, okay, rated steam condition, meaning that definitely they will give a higher efficiency. So that's one way for you to improve efficiency of your process, I guess. This is one. Number two, obviously you need to use a closed loop system, because it's better for you to reuse the spent steam, okay, instead of throwing it away. So it's no brainer if you use an open loop steam turbine system. So that's number two, okay, use a closed loop system. And the second one is they run at high temperatures. An example, as I have mentioned, GE steam turbine, Siemens steam turbine, you can just go and look at it at the manufacturer's specification. You'll see that they can run at high temperatures and high pressures. So 287 is nothing, I guess. So, but that's what the example says. So I'm just going to follow. This is the link to the brochure that I got, Siemens Energy. This one is just a steam turbine brochure. This one is just example. This is just a reference where I got this thermal efficiency of power plant. So yeah, that would be all from me. I hope you like the videos. I'll try to run Aspen maybe next 2 weeks, I guess, but we'll see. Anyway, if you like the videos, give it a thumbs up, consider subscribing to my channels, and I'll see you guys in the next video. Bye bye.